We can think of water as an example. If we consider the two-dimensional space parameterized by temperature and pressure, there are one-dimensional curves where two phases can be in stable equilibrium with one another, either ice in contact with water or water in contact with steam. So in particular, let's talk about water and steam. There's this curve in the PT space where the water and the steam in mechanical, thermal, and diffusive contact can be in stable equilibrium with one another. There's a line of transitions between water and steam which terminates at a critical point at a value of the temperature and pressure, which I'll call the critical temperature and pressure. We can also consider the coexistence of phases in the pressure-volume plane. And then I can draw isotherms, curves of constant temperature. And when the temperature is low enough, there will be a region of finite width and volume in which the pressure is a constant. That's the region in which the gas and the liquid are in contact and in equilibrium at sufficiently high temperature, that is, above the critical temperature. There is no such transition. And there's a special value of the temperature, a so-called critical isotherm, where the phase coexistence region begins. So this is the critical value of the temperature, this isotherm, which separates the low temperature region in which we can have coexistence of water and steam, and the high temperature region above this critical point where there's no transition between water and steam. One can go smoothly from one to the other. And I'll talk about the value of the pressure and the volume on this critical isotherm at this point where the phase coexistence region opens up as P sub C, P critical, and V critical. So if we have water in contact with steam, there's water vapor above liquid water, and as we compress, reducing the volume at constant temperature, moving along the critical isotherm in this direction, we reach the point where phase coexistence begins, water forms in the chamber, and then as we continue to reduce the volume, the pressure stays constant, more and more of the vapor is converted to water until finally it's all water, and then as we continue to compress further, the pressure shoots up again. So since the two phases are in thermal, mechanical, and diffusive equilibrium, the chemical potential, or Gibbs free energy per particle, as a function of temperature and pressure for the liquid is equal to the chemical potential as a function of temperature and pressure for the gas along the coexistence curve. And from that we derived an expression for the slope of the coexistence curve as a ratio of the discontinuity in entropy to the discontinuity in volume across the curve at coexistence. So when we boil water, we add heat to the water to convert it to steam, increasing its entropy per particle. There's latent heat in the transition, so delta S is positive. And of course the steam has lower density and therefore higher volume per particle than the water, so there's a positive delta V. the slope is positive. Delta S and delta V are both positive. Now we'd like to understand why this phase coexistence occurs more from a microscopic viewpoint. So I'm going to describe a kind of naive, fairly simple model of non-ideal behavior in a gas. Within that model we can understand better why a transition to a liquid would occur. The model should incorporate interactions among the molecules which make the molecules want to clump together and form a liquid. So those interactions should be attractive, at least at long range. But to make the model more realistic, we'll also include some short distance repulsion so that the molecules can't sit right on top of one another. So we want to understand how a deviation from ideal behavior of a gas, the ideal gas law PV equals n tau, will be modified so that formation of a liquid will be favored at low enough temperature. So we'll consider some two-body interaction between particles. So potential energy of particle pair as a function of separation between the particles. We'll imagine a potential that looks kind of like this. It turns on very sharply at short distances. There's a hard core. So we can think of the molecules as hard little balls which we can't press any closer together than some minimum distance. But at long distances, there's some attractive force bringing them together. And that's described by this negative potential energy. So we'll consider modifying the ideal gas law in two ways. The first way is that to take into account the hard core, we'll exclude some volume. So each one of the molecules will have places that it can't go. It can't go too close to the positions of the other molecules. So we'll replace the volume by volume minus number of particles times B. Think of B as the excluded volume per particle. And for long-range attraction, there will be some additional contribution to the internal energy, which will be a sum over pairs of particles. Label the particles by an index, taking values like I and j. So consider a pair of indices, I and j. The potential energy of that pair of particles I'll call Vij, and we'll imagine that we can think of the particles as being described by a uniform density of particles. So I can write that potential energy as 1/2 an integral over the position of particle 1, position of particle 2, density of particles at x, density at y, that is number per unit volume, times potential energy. Sorry, here V means potential energy, not volume, as a function of the separation, x minus y. And we'll imagine, although in reality the density can fluctuate, and those fluctuations are actually important, and we'll be talking about them more later, we'll consider the density to be uniform as a first approximation, sometimes called mean field theory. The idea of mean field theory is that each one of the molecules is actually interacting with many other molecules. But we can describe the interaction by averaging over all the other molecules. Yeah.
So is M like the number of particles or the concentration or something?
Yeah, it's the concentration, which in principle could vary from point to point. So it's the local concentration equals number of particles per volume. So if we think of the particles as having precisely defined positions, it would actually just be a sum of delta functions, with the delta function supported at each one of the positions of the particles. But we average over many particles, and we can think of dividing the system up into cells, each containing many particles, and by what I mean by n is the number per unit volume in each cell. In principle, it could vary from cell to cell, right? That's what I mean by fluctuations. But we're not going to worry about that. We'll just assume the density is uniform, and I can write down an expression like this for the potential energy coming from the long-range attraction. Yeah.
So the volume, the V of x, so how do you explain the V of x minus?
Well, so I'm saying, so this is this is a way of rewriting the sum over pairs of particles of the potential energy between the particles. If you thought of n, it's okay?
So yeah, that's the potential.
Right, yeah, sorry, too many things want to be called V. Yeah. It's the potential energy of a pair with separation x minus y. So if I pull the concentration out of the integral, because we're going to take it to be a constant, I can write this as a contribution to the internal energy, which is 1/2 concentration squared. So if I change variables, integrate over x minus y and integrate over x, there's a factor of volume that comes from integrating over x. And then I'm left with an integral over a position of the potential energy function. So, in principle, that could diverge if the potential energy doesn't fall off quickly with distance, but let's suppose it does fall off quickly enough that it's a convergent integral. It's something with the dimensions of energy times volume. I'll just give it a name. I'll call it minus 2a. And so, since concentration is number of particles per volume, I can write this as minus a, number of particles squared divided by volume. I want to consider a to be positive, corresponding to the potential energy being negative because it's an attractive interaction. Okay? So, my naive model, I'm going to continue to apologize from time to time for its being an oversimplified model, of the gas, which I'll call the van der Waals model, or, well, I guess that's what I'll call it, the van der Waals model, is obtained this way. I consider the expression for the free energy that I would have in the ideal gas case, but now replacing the volume by the included volume, what's left over after I subtract away the volume occupied by all the particles, and then the additional contribution coming from the attractive interaction piece of the internal energy, which is minus a n squared over v. Then if I want to find the pressure, I can differentiate the Helmholtz free energy with respect to volume with temperature and number of particles fixed. And from the first term, I just get the usual expression for the ideal gas pressure, except the volume is replaced by the included volume. So I have n tau divided by not V, but V minus NB. And then I have the additional contribution from differentiating the last term, which goes like 1 over volume. The differentiating gives a minus sign, but there's a minus sign here and a minus sign here. So that's a negative contribution to the pressure if A is positive, minus N squared over V squared times A. Okay. So I'll call this the van der Waals equation of state. In fact, let's rewrite it in the following way. We're going to replace the ideal gas law by pressure, put the n squared A over V squared on the other side, so pressure plus n squared over V squared A times the volume minus the excluded volume, V minus NB, equals n tau. And it's not a particularly good description of a gas at high density. It's okay for low density, but so is the ideal gas law. Okay approximation for dilute gas. Rather poor approximation for a dense gas. Nevertheless, we're going to use it even when the gas is dense. Again, the idea is just within the context of a model to understand why a gas would liquefy, not necessarily to give a good quantitative description of what happens in real gases when they liquefy. Okay, so we can think of this equation as determining the volume when we specify the temperature and the pressure. But in fact, to find the volume now, we have to solve a cubic equation. For given temperature and pressure, find volume. By solving cubic equation. In fact, for convenience, let me multiply by V squared and divide by pressure. And then I can rewrite it. The first term becomes V squared plus N squared over P times V minus NP is equal to N tau V squared over P. I wanted to write it in a form in which all the powers of V are positive, or non-zero, positive or 0. So if I expand that out, the cubic equation that we have to solve to determine V becomes V cubed minus there's an NB V squared and an N tau over P V squared, which we'll subtract to put it on the other side. So minus NB plus N tau over P V squared. And then there's a linear term in V here, so plus N squared A over P V, and then this constant term for multiplying these together, minus N cubed AB over pressure. Now, a cubic equation can have either one real solution or three real solutions. can be 1 or 3. And what's going to happen as we change the temperature is there will be a transition from high temperature where there will be a single real solution and the volume is uniquely determined. At low temperature there will actually be 3 solutions. The transition between the two we're going to identify with this critical point where the line of phase transitions ends and the coexistence between gas and liquid goes away. So this equation, if you want to think of it as defining the pressure as a function of volume, for various values of the temperature, has a critical temperature, a critical isotherm, tau c, which separates higher temperatures for which the pressure as a function of volume is monotonic, and so for each value of the pressure there's a unique value of the volume. At lower temperatures it's not monotonic. So for a given value of the pressure there can be 3 values of the volume that solve the equation of state. So as I just said, if we think of the behavior in the pressure-temperature plane, at sufficiently low temperature there can be a transition or coexistence. At sufficiently high temperature there is no coexistence, and we want to identify this point, the critical temperature and pressure, as this point of inflection on the critical isotherm, where P as a function of V becomes has vanishing first derivative, has zero slope. So this is actually going to be the critical volume and critical pressure, this point of inflection along the critical isotherm. Okay? Now, when we're on the critical isotherm, yeah.
Why is that going to be the critical volume and critical pressure?
Well, we're going to understand that as we proceed. Okay. But what we're going to see is that the right interpretation of the existence of 3 solutions for the volume as a function of the pressure is that 2 different values of the volume can be in stable equilibrium with one another, and those are going to correspond to the gas and liquid phases that can coexist with one another in equilibrium. Those will be these 2 solutions, the ones with the lowest and highest volume that can coexist with one another. This one actually is unstable. Okay? And so what would happen if the volume were in between these 2 values of the volume is that instead of being homogeneous, the system will want to split up into 2 different phases which are in equilibrium with one another with different values of the density. Okay, but that's what I want to explain in the rest of the lecture. So the details, actually, of the van der Waals equation of state, as I've already emphasized, are not so important. But this qualitative feature, that there are high temperature isotherms for which the pressure is a monotonic function of the volume, low temperature isotherms for which it's not monotonic, that's the generic feature that we want to capture and understand what its implications are. That's much more general than this particular equation of state that we've written down. So on the critical isotherm, there are three degenerate solutions. It separates where the three real solutions come together and become one real solution, right? So for tau equals tau c, the equation of state has a threefold degenerate solution at the critical volume. So it's just V minus V critical cubed equals 0. So if I expand that out, V cubed minus 3VC V squared plus 3VZ squared V minus VC cubed, I can just match powers of V, the coefficients of powers of V, between that equation and this one when T and P are the critical temperature and pressure. Okay? Critical temperature and pressure means we're expanding this cubic with an inflection point at the origin around the origin. So if we do that matching, compare this with Vigual's equation, the coefficients of V squared are 3VC here in the equation I wrote down earlier, n times E, n times B, plus n times the temperature, which is now the temperature on the critical isotherm, divided by the pressure, which is now the critical pressure, the value of the pressure at the point of inflection. And if I match the coefficients of V, 3VC squared is equal to n squared A over the pressure at the critical point, PC. And if I match the constant terms, critical volume cubed is n cubed AB divided by critical pressure. And now I can use these equations to express the critical pressure and the critical temperature in terms of the parameters of the van der Waals equation, A and B. Particularly if I take equation 3 and divide both sides by the corresponding sides of equation 2, I have 1/3 VC when I divide VC cubed by 3VC squared, and that's equal to NB. That's what I get when I divide this expression by this one. The A's and the PC's divide out, and I just have NB. So that tells us what the critical volume is. The critical volume is equal to 3NB. Remember, the excluded volume occupied by all the molecules is NB. So that means that at the critical volume, the gas is quite dense. The separation between particles is comparable to the size of the particles. The volume is not much more than the excluded volume. Mm-hmm.
Here you have 3 equations, but you only have 2 equations.
Yeah, that's right. Well, in principle, I could set them in terms of A, B, and N, but PC and TC are actually intensive quantities, pressure and temperature, and so are A and B. So N is going to drop out.
Okay.
Yeah.
Does that have anything to do with reappointment?
Well, and I'm using two pieces of information. I mean, it's true.
So I'm afraid you're going to overdetermine. That's what they're not going to be consistent. What makes them, what guarantees them to be consistent?
Okay, well, maybe you'd prefer to say it this way. I can express critical volume, critical pressure, and critical temperature in terms of A, B, and N. Okay? And what we expect to find is that the volume will scale like N because it's intensive, and the pressure and temperature will be independent of N. So it's, right. Yeah, that would have been a better way to say it. In fact, we've already found the critical volume is N times the intensive parameter B. Okay, so now if I want to find the critical pressure, we can come back to equation 2. But substitute what we've now found for V critical. So it's 3 times 3NB squared equals N squared A over critical pressure. So the critical pressure is equal to N squared A times the reciprocal of this, which is 1 over 27 N squared B squared. So like I promised you, the N's divide out, and this is just A over 27B squared for the critical pressure. And now we can find the critical temperature from the first equation. So subtract this from both sides. The critical temperature is the critical pressure, which we now know, divided by N. 3 times the critical volume that we now know, minus NB. So 3 times the critical volume is 9NB. This is 8NB. The critical pressure is A over 27B squared. And we have 1 over N here, and then 8NB. So the N's divide out, as do one of the B's. And the critical temperature is 8A over 27B. Remember, B has the dimensions of volume, and A has the dimensions of energy times volume. So this is energy. Okay. So now, that's fine. I mean, we had these parameters that came from microscopic physics, and we've been able to find the parameters characterizing this critical isotherm in terms of A and B. So there's a strategy, which is a good thing to do in general, and so we'll do it here, and that is to express our equation in terms of quantities that can actually be directly measured, not A and B, but rather the properties of the critical isotherm. So we'll re-express the van der Waals equation in terms of quantities that are in principle measurable. The volume, the temperature, and the pressure on the critical isotherm. So, just rewriting the van der Waals equation I had written down earlier. Pressure plus N squared A divided by V squared times volume minus the excluded volume NB equals N tau. And now let's substitute in in effect, what we know about A and B. Well, here's a convenient way to do it. Let's divide by PC and BC. So this factor becomes V over VC minus NB over VC. This, when we divide by PC, becomes P over PC plus, and then it'll be convenient to write VC squared over V squared times N squared A divided by VC squared PC. And then on the other side, tau over tau C. And then after dividing by tau C, I'll also multiply by tau C. And since I divided the other side by VCPC, I have VCPC in the denominator. And now all of these quantities, NB over B critical, N squared A over VC squared PC, and N tau C over VCPC, are dimensionless and intensive quantities. They're just numbers, in other words. And we can write down what they are. Since the critical volume is 3 times NB, NB over VC is equal to 1/3. N squared A over VC squared PC is equal to N squared A. And then 1 over VC squared is 1 over 9 N squared B squared. VC is 3NB. And 1 over PC is 27B squared over A. So the N's, the A's, the B's, and the C's divide out. And I just have 27 over 9, 3. And then we have this to evaluate. N critical temperature divided by critical volume, critical pressure. N, and then A over 27B for the critical temperature. 1 over 3NB, the 1 over the critical volume. 27B squared over A for 1 over the critical pressure. So again, the A's, the B's, and the N's divide out. And so do the 27. So all I have is 8/3. So in other words, the van der Waals equation of state, as written here, becomes volume normalized by critical volume minus 1/3 times pressure divided by critical pressure plus 3 critical volume divided by volume squared is equal to 8/3 temperature over critical temperature. And this is called the law of corresponding states. Now the concept is a good one. We've taken this equation, which has some microscopic parameters, but then we've re-expressed it in terms of things that can be directly related to measurable quantities, to experiments. And so the equation in this form ought to apply to any fluid that's described by the van der Waals equation of state, no matter what the values of A and B. So the concept is to find a universal property which will apply irrespective of the microscopic detail. So that's a good concept. But the equation is a rather bad equation. In other words, the law of corresponding states isn't very well satisfied by the critical points of different gas-liquid transitions, and we're not surprised because the van der Waals equation of state itself was kind of a crude approximation, not to be trusted when the fluid is dense, and yet we have used it to describe the critical point where the fluid is dense, where the volume is close to the excluded volume. Okay. But we're going to continue to try to make use of the philosophy of identifying in our model properties that are universal and will apply more broadly than the model itself. Okay. In other cases, with greater success than we met here. Actually, maybe I shouldn't be erasing this, because what I want to do now is come back to the interpretation of these isotherms, where the pressure is not a monotonic function. Of the volume. So the pressure is given by, in effect, a cubic as a function of the volume when the temperature is less than the critical temperature along an isotherm. So there are a couple of critical points where the pressure as a function of volume has our vanishing first derivative. And in between, dp dv is positive. Well, dp dv being positive is a sign that we've done something unphysical. So we have a fluid and we're pressing down on it, reducing its volume. Normally, as we compress it, the pressure goes up. If dp dv is actually positive, the more we compress it, reducing the volume, the more the pressure goes down. Now we push harder and harder on the fluid, and it pushes back less and less. So we push more, fluid pushes less, so it's unstable. It'll just collapse. We're not really in a stable equilibrium. For stability, we want dp dv to be negative. Or at least less than or equal to 0. Now here's another way of looking at it. So we have a system in contact with a reservoir at a specified temperature, and the most probable configuration is the one that maximizes the entropy of the world, which means it minimizes the free energy. So I can say that the free energy total, the free energy of the system plus the free energy of the reservoir, should be stationary. So in particular, if I consider the system in mechanical contact with the reservoir, derivative of free energy with respect to volume for the system or maybe I should say it this way, for system at constant temperature minus derivative of free energy with respect to volume for reservoir at constant temperature times change in the volume of the system should be equal to 0. So there's no first order change in the total free energy, and since the derivative with respect to volume is just minus the pressure, this is minus the pressure of the system. This is the minus means it's plus the pressure of the reservoir. So in equilibrium, the pressure of the system is equal to the pressure of the reservoir. That's the condition for mechanical equilibrium, as we've discussed. But we also should check that the free energy is really at a minimum, not a maximum. Right? It's not enough for it just to have vanishing first derivative. Its second derivative should be positive. So if we want F total to be minimized, then its second variation should be non-negative. So if I consider differentiating again with respect to volume, the first derivative of the free energy is minus the pressure of the system plus the pressure of the reservoir. The reservoir is huge, so when we change the volume, it doesn't change. So its first derivative is 0 with respect to volume for a very large reservoir. So this is equal to minus derivative of pressure with respect to volume for the system at constant temperature. And we want that to be non-negative for stability, so that the free energy is really minimized rather than maximized. So, the conclusion again is for stability, derivative of pressure with respect to volume for the system should not be positive. And that's not true here. We have dP/dV positive in between these two values of the volume. Question?
Isn't it only a minimum when it's strictly?
Well, yeah. If it's equal to 0, then we have to consider even higher derivatives to know whether it's a minimum or a maximum. It's possible that it's equal to 0, but say the third derivative vanishes and the fourth derivative is positive, it would still be stable. But if it's negative, we're in trouble. And actually, this is similar to something that we discussed earlier. I think there was a homework problem about this. In the case of a system in thermal contact with a reservoir, stability requires the heat capacity, the derivative of energy with respect to temperature, to be non-negative. If the heat capacity were that's right, to be non-negative. If the heat capacity were negative, what would it mean? It would mean that when heat flows from the reservoir, into the system, increasing the system's internal energy, its temperature would go down. So there's flow of heat from the reservoir into the system gets colder, so there will be more flow of heat from the reservoir to the system, and so on. That condition, again, we can view as the requirement that we're really at a stable equilibrium. We found the condition for thermal equilibrium in contact with the reservoir by demanding that the total entropy is maximized, which means that not only do we want T sigma total to be equal to 0 at the maximum, but also the second variation of the entropy to be negative. So we're really at a maximum. So the second derivative of entropy with respect to internal energy with volume fixed, which is the derivative with respect to energy, derivative of entropy with respect to energy, which is 1 over temperature, which is minus 1 over tau squared derivative of temperature with respect to energy, which is minus 1 over tau squared times 1 over heat capacity. We want that to be non-positive, so that requires the heat capacity to be non-negative for stability. That's the same kind of argument. Okay, so we've established that there's something unphysical about the state described by this isotherm where dP/dV is positive. It's unstable, but unstable to what? What state does the system want to be in instead? So again, let's look at the isotherm. And let's consider the free energy as a function of the volume with the temperature fixed, which means we can integrate along the isotherm to see how the free energy behaves when we change the volume. Since we know the pressure is minus derivative of free energy with respect to volume at constant temperature, we can write the free energy as a function of the volume as minus the integral P/dV along the isotherm plus some constant of integration. So what does the free energy look like if we plot it as a function of the volume? Well, it looks kind of like this. I'm going to draw a straight line to kind of guide the eye. That's a little too exaggerated. The pressure, which is the derivative, minus the derivative of the free energy with respect to the volume, is always positive, so the derivative is always negative. But if we follow the isotherm, which means we're considering a homogeneous phase, the volume well, the free energy as a function of the volume is going to be concave down. It's going to have a negative second derivative in this region, and it's positive here. So here, where dp dv is positive, f of v is concave down. But suppose, instead of following this curve which describes the free energy as a function of the volume for a homogeneous phase, I instead mix two different phases. So here, there's a volume, call it V1, and here V2. And if I consider a mixture of this phase and this phase, with a fraction of all the volume described by this phase, and the remaining volume described by that phase, then the Helmholtz free energy will just follow this straight line. Where we are on the straight line determined by what fraction of the total volume is in phase 1 and what fraction is in phase 2. Okay? So this is what the free energy would look like in the mixed phase. And this is the free energy in the homogeneous phase. So in this region where the state is unstable, we can get to lower Helmholtz free energy by taking a mixture of this phase and this phase. And since our goal is to minimize the Helmholtz free energy for each value of the volume, we should be following the straight line curve in this region, not the curve for the homogeneous phase. Yeah?
When you say homogeneous, you mean...
I mean, it's not separated into two different phases in coexistence with one another. It's like all liquid or all gas. So if we consider reducing the volume, we want to go to the minimal free energy. So here we want to follow the homogeneous curve. But when we get here, we can do better by starting to mix in a little bit of this phase. Then we can follow the straight line as more and more of the available volume is converted to the higher volume phase, okay, until it's been converted completely, and then we follow the homogeneous curve again. Okay? So that picture enables us to see how we should pick the pressure, how we should interpret this minimal free energy state described by this isotherm. So I claim we should do the following thing. The pressure where phase coexistence occurs, I'm going to choose so that the area below the value of the pressure on the critical isotherm matches the area above this value of the pressure on the critical isotherm. Now, how do I know that? Well, there are two different ways of getting from this point to this point. One is to integrate along the isotherm, and the other is to mix the two phases. So we want to answer the question, for what value of P does coexistence occur at a specified value of the temperature? These two points have the same pressure because the slope to the F versus V curve is the same at both points. So if we follow this curve, which is a straight line in the free energy versus volume function, we're keeping the pressure constant. So let me call the free energy here F1 at volume V1 and the free energy here F2 at volume V2. So I can write F2 as F1 minus the pressure at which there's coexistence. That's the slope of the dotted straight line, times the difference in volume, V2 minus V1. But I can also write it as F1 plus the integral of the first derivative of F with respect to V along the isotherm. So in other words, F1 minus the integral P dV along the isotherm. Well, the two have to agree. There are two ways of getting from this point in the plane to this one. One is to follow the straight line, and the other is to integrate along the isotherm. But they both take me from here to here. So that's what this equation says. So this means that the pressure of coexistence times the change in volume between the two phases, V2 minus V1, is equal to the integral from one volume to the other of the pressure as given by the van der Waals equation of state, that is, along the isotherm dV. And that's just what I was saying here. This is V1 and V2. This is the pressure of coexistence. The area under this horizontal line is P coexistence times the change in volume, V2 minus V1. The area under the isotherm is this integral, and that's equal to P coexistence times V2 minus V1. But since the areas under the two curves are the same, that means this deficit has to match this surplus of area. So these are equal areas if we choose the horizontal line to be at the pressure where coexistence occurs. So that way of choosing the pressure of coexistence so that the free energy is really minimized is called the Maxwell construction, or equal area construction. There's another way of describing this using Gibbs free energy instead of Helmholtz free energy, which is also in its way instructive and maybe a little bit easier. We can think of expressing volume as a function of pressure, except along the isotherm it's not really a function, it's multi-valued. If this is the coexistence pressure, then volume as a function of pressure looks kind of like that. Yeah?
Here, if it's equal area, wouldn't
Right. So integral PdV means the integral of this function, this cubic function, along the isotherm. And I'm saying that's equal to the integral of this constant function, where the constant is the coexistence pressure. The two integrals being equal is equivalent to saying that this area, where the isotherm dips below the coexistence pressure, matches this area where the isotherm exceeds the coexistence pressure. So if we think about Gibbs free energy instead, remember, in diffusive equilibrium, the Gibbs free energy of the liquid has to be equal to the Gibbs free energy of the gas. And dG is given by VdP, the partial derivative of Gibbs free energy with respect to pressure with temperature fixed is given by volume. So if these 2 points, the two values of the volume V1 and V2, are the gas and liquid phases which can be in diffusive equilibrium with one another, they must have the same value of the Gibbs free energy. So we want the integral of dG from 1 to 2 to be equal to 0. Okay, so the Gibbs free energy here is equal to the Gibbs free energy here. Or in other words, when we integrate along the isotherm, the integral of V dP is equal to 0. So here dP is positive, here dP is negative. The integral of V dP equals 0 is the same as saying that this area matches this area. It's the same picture I drew here, except turned on its side. So the interpretation is, in this case, that we're finding the condition for the two homogeneous phases described by this point and this point to have the same Gibbs free energy, so they can coexist in diffusive equilibrium. And here, for each value of the volume, we try to choose the mixed phase, which gives the lowest possible value of the Helmholtz free energy, and we can do that by drawing this lowest possible curve, which is tangent to the Helmholtz free energy along the isotherm at 2 points. Now notice that although the two phases, the gas and the liquid, have the same Gibbs free energy, the derivative of the Gibbs free energy with respect to pressure in this case doesn't have to match. The slope here and the slope here can be different. G liquid equals G gas, but first derivatives can be different. Actually, it's not really this. The first derivatives are the first derivative is actually the volume. So obviously there's a volume discontinuity. So the first derivatives being different just means these two volumes are different. So in the case of the Gibbs free energy, regarded as a function of temperature and pressure, remember its derivatives. With respect to temperature with pressure fixed, that's minus entropy. And with respect to with respect to pressure, with temperature fixed, that's equal to volume. So, as we've already discussed, sigma 1 doesn't have to be equal to sigma 2. V1 doesn't have to be equal to V2. The entropy per particle is different in particular, so there's latent heat in the transition. The volume per particle is different, so there's a density discontinuity. In particular, the liquid is more dense than the gas. So we say that a phase transition is first order. If first derivatives of free energy, in particular Gibbs free energy, are discontinuous at transition. Along the coexistence curve, the Gibbs free energy of liquid and gas agree, but the first derivatives disagree. So, although the details of the van der Waals equation of state are not really fundamental, the observation that we've made here is a much more general thing, that when we have an isotherm in which, say, the volume as a function of pressure isn't really a function, or the pressure is not monotonic, what it means is, to get the lowest possible Helmholtz free energy, we'll be better off choosing a mixed phase with two different values of the volume mixed together than a homogeneous phase. And that's how first order phase transitions occur. Okay, let's talk a little bit about metastability. So again, if we look at pressure as a function of volume, temperature below T critical, the naive equation of state relating the pressure and the volume is not monotonic. The actual physical equation of state is one in which the pressure remains a constant coexistence pressure between two different values of the volume. So suppose we start out here at large volume, so we have vapor, and then we start to compress the vapor at this fixed temperature described by this isotherm. Eventually we reach this value of the volume where the stable phase is the one which is a mixture of gas and liquid, here say. But when we cross this point, we're not yet in the region where the system is unstable. Here we still have dP dV negative, So the system has a positive compressibility. When you push on it, it pushes back further. But we're not in the stable phase. Similarly, if we're over here and we have the liquid and we start to increase the volume along the isotherm, keeping the temperature fixed, eventually we get to a large enough volume so the stable phase is a mixture of vapor and liquid. But we still have positive compressibility, not an unstable system. So in this case, we say we have a superheated liquid. I've been describing it as a change with the temperature fixed, but superheated liquid means we've got liquid, but the stable phase would have some gas. So the liquid really wants to boil in order to find its most probable configuration. And here we say we have a supercooled vapor. So the system, it's all vapor, but if it were in its most probable configuration, some droplets of liquid would form. But there's some time scale for that to happen. If we were really in equilibrium, we'd have droplets of vapor, and here we'd have bubbles of gas forming in the liquid. But it takes a while for the bubbles of gas to form, or the droplets of liquid to form. So why is that? Why doesn't it happen right away? Suppose we have a supercooled vapor. There's a vapor. And in principle, there should be some droplets of liquid. So suppose the droplets are really small. What happens to them? Well, is there something else that's important? If you have a bubble of gas in a liquid or a droplet of liquid in a gas, that's important aside from which is the thermodynamically more stable phase? Well, in order to understand why the superheated liquid doesn't boil right away, or the supercooled vapor doesn't form droplets right away, we have to take into account something that we haven't included so far, and that's surface tension. If you have a little droplet, and you imagine it growing a little bit, which means that more of the surrounding vapor is being converted to liquid. How does the energy of the droplet change? Well, what work is being done? We can say that the droplet has pressure, and when it expands, the droplet is doing work, but there's something else, which is that there's some tension on the surface of the droplet where it meets the vapor. It's like a little balloon, and when we expand it, then we have to do work against that tension. We have to stretch the surface. And stretching the surface gives another contribution which depends on the change in the area of the droplet to the work done. So I'll call gamma the surface tension. And this is the change in the area. So, suppose little g is the difference between the Gibbs free energy of the gas and the liquid divided by the volume. Well, if we were really in the equilibrium configuration, that would be 0. But in the superheated liquid or the supercooled vapor, they don't exactly match. One phase or the other is favored. And so we can gain some bulk free energy by converting some of the vapor, say, to a droplet of liquid. The change in the Gibbs free energy when a droplet forms which has volume V is minus G times the volume. So it's a good thing to make liquid because that's favored in the thermodynamically stable phase. But it's a bad thing to make area because that costs you work that you have to do against surface tension. So if the droplet is spherical, which is actually what it will prefer to be in order to have the smallest possible area and therefore do the least work against surface tension for a given volume, and the energy cost of making a spherical droplet is just the volume of the sphere, but with a minus sign, 4 pi over 3 r cubed, the volume of the sphere, times the Gibbs free energy per unit volume, plus 4 pi r squared times the surface tension. So when the droplet forms, if it's small, then there's going to be some positive cost in Gibbs free energy for making the droplet. The surface tension dominates when r is small. But eventually, when it gets big enough, the gain in Gibbs free energy by forming liquid overcomes the cost arising from the surface tension and the curve turns over. But it means in order to make a droplet which is favored to grow larger, it has to exceed some critical size. And there's going to be some height in Gibbs free energy that we have to overcome to make that droplet which is large enough to grow. Little droplets, because of their large surface tension, will just want to shrink away again. Okay? Only when a droplet gets big enough will it be able to grow. And it's going to take a while for a large droplet to form as a result of a fluctuation. We can see what the critical size is and what the height of the barrier is just by minimizing this function. So if we say DDR delta G equals 0 to find where the slope of the Gibbs free energy cost as a function of R goes to 0, this is equal to minus 4 pi critical radius squared times Gibbs free energy per volume plus 8 pi critical radius times surface tension. So that means that the critical radius solving that equation will want to be 2 gamma over little g. So if little g is small, then we've just gone a little bit past the point where the droplet wants to form. Then it's going to be a large droplet, and correspondingly it'll have a large Gibbs free energy. The height of the barrier for the critical droplet, the one large enough to grow, I just plug that value of RC back into this function. So it's equal to 4 pi gamma cubed over g squared. Then from the minus 4 pi over 3 r cubed, I get this 2 cubed, so it's minus 8 thirds. And then plus 4 from squaring the 2 in the second term. So this is plus 4 thirds times 4 pi, or 16 pi over 3 gamma cubed over g squared. So we're going to have to pay a price in Gibbs free energy, this big a price, before we can make a droplet which is big enough. And so we have to wait for a fluctuation to occur in which a large deviation from equilibrium in Gibbs free energy occurs. So the rate of droplet formation go like some characteristic time scale for fluctuations, which I won't try to estimate because that's harder, 1 over that time scale, times the probability of a fluctuation in which the entropy fluctuates from the most probable configuration by a large amount. So in other words, the cost of a fluctuation will go like e to the fluctuation in the entropy away from the equilibrium value. And since we're considering a process at constant pressure and temperature, where dg is equal to minus sigma d tau, well, I want to actually, let me not say that. This cost, if we're considering something at finite temperature, would go like e to the minus the cost of a fluctuation in free energy divided by temperature. And if we're considering a process in which the pressure is fixed too, the probability is going to depend on how large a fluctuation there is in the Gibbs free energy normalized by the temperature. So since the droplet has a big free energy when we supercool a little bit or superheat a little bit, where that Gibbs free energy difference between the two phases is small, it can take quite a long time for the superheated liquid to boil or the supercooled vapor to have droplets form. So there's a nice theory of metastability. It doesn't actually work very well in explaining how long it takes a superheated liquid to boil or a supercooled vapor to condense. And the reason is we've left out some other complications which in practice are really important. Theory does not work well when compared with experiment. And there are two main reasons why. So one is a phenomenon called wetting. What that means is when you really cool a vapor, it tends to be favored for droplets to form that cling to the surface of the container. So there's some kind of tension or attraction for the liquid when it's in contact with the walls, which is really the dominant effect, which determines when it wants to condense. It's not just the bulk behavior, but the way the vapor interacts with the container that's important. And the other big issue is impurities. What often happens in practice is that there's some dust or something in the vapor, and so the droplets prefer to form by nucleating around the fragments of dust that are suspended in the vapor. That's what happens when you seed a cloud in order to make water vapor form and induce it to rain. So there's a nice theory of metastability which comes from thinking about the deviations from equilibrium when the system fluctuates in the supercooled or superheated region, but because of various practical complications, it doesn't usually explain the data very well. Okay. Next time I want to talk about second order phase transitions.